Okay.
Is it okay now?
Let's go.
Okay. Good. So, sorry. Okay, can you hear me well? Okay. So now we have implemented the code for one of the three mandatory components to describe and run a Geant4 simulation, which is the detector constructor that basically defines the materials and the geometry hierarchy that describes of our experimental setup. The second mandatory component is the so-called physics list. And we will review it here rather quick, hopefully before we leave today. So today in this presentation is very short. We will review what is a physics list, what is the interface that is implemented that we should implement, and what are the modular and reference physics lists provided by the Geant4. So what is a physics list? Is an object that should specify the particles that will be used in the simulation, together with the physical processes that describe how each particle interacts with the materials, with the matter. Is one of the three mandatory objects that the user must provide to the run manager. In case of a Geant4 application, the run manager again is just as a bucket where you will put the detector construction, the physics list, and the actions, the user actions. So the physics list is the second object that we will have to provide. The user can choose what physics and particles will be used, but doing that requires a deep understanding of the physics required to describe properly the problem, and the omission of relevant particles or some particle or physics interactions will lead, here in the slide sees poor modeling results. It could be catastrophic. So if a priori you don't know, we will review at the end of this presentation and later in the application that we will use. Geant4 also provides for many years now some reference physics list, which is not the final truth. It's simply something that you can use out of the box, but still it's the responsibility of the user to know what is happening. And there are dedicated user guides for that, as we will see later. Why do we need a physics list? Well, Geant4 does not provide by default full physics. There are different recipes if you want to describe several models. You can look, for example, how many Compton models to describe the Compton interaction exist, or ionization, depending if the material is solid, if it is a gas, if it is solid, up to which level of description you want to implement. So Geant4 provides some processes, some of them ready to use, but in general, what Geant4 will provide is an interface. And if you really want to use something custom, nothing prevents you from defining your own process, in addition to the ones that Geant4 defines. But that, again, as I said before, that requires deep understanding. So Geant4 provides an atomistic approach to this and allows you to take, for example, a reference physics list, which is rather complete, and maybe replace or remove some of the processes if you think that is best. But the last word is yours, and it's your responsibility to know what you are choosing. The physics list, as in case of the detector constructor, is implemented as using an interface. So every class that is a physics list should derive from G4V user physics list, and it has to implement two interface methods: construct particle and construct process. The construct particle method, as you may anticipate, will have to describe to register into Geant4 what are the particles that may happen during the simulation, not only the primary particle that you will inject, but also all the potential secondary particles. If you are forgetting to register some of these particles, they will never be created, and they cannot be created or handled anyhow during the simulation. For example, if you forget, in case of high energy physics, if you forget some of these rare particles, a Xi particle, and you don't declare it in the construct particle and any process can create it, this particle will never exist. In your simulation will never be taken into account, and the effects of this particle will never be simulated. I cannot think much about any other cases in nuclear physics or medical physics because the set of particles that are being used is more reduced, but it can happen. If you forget to register the gamma rays, the gammas, you will never see any particle or any process will be able to create gamma rays. As I was saying, you have to register the particles in this construct particle method one by one by calling, for example, these methods, the definition method of each particle, or also Geant4 provides some helpers. For example, you can construct particles by bunch if you want. The construct process is the other interface method that will define a list of physical processes to be used in the simulation for every particle. So I don't know if it was here. Yeah. So this is an example of how to attach some processes. In this case, if the particle is a gamma, associate to this gamma this process gamma conversion. If it is an electron, associate to the electron the Bremsstrahlung process, and so on. Geant4 provides some of these processes, but nothing prevents you from implementing new ones using the interface for, in this case, for process, or nothing prevents you from implementing a new particle in case you want. But for us in this course is too complicated. You can take the advanced course in autumn that will show you how to do it with a bit more detail, or at least how Geant4 has implemented this in a more detail. Defining the particles and processes one by one is a bit complicated. So Geant4 introduces an intermediate step, which is a modular physics list. And it allows you to take some modules of Geant4 that, for example, already define a subset of particles among all the ones that are defined, exist or Geant4 provide, and the associated processes. Some of the processes that are already provided built in by Geant4. So for example, you can register only electromagnetic, the particles associated with electromagnetic physics, or electron, positron, gamma, and their corresponding processes. And you can do the same, for example, for some hadronic physics or for radioactive decay, and so on. Transportation is a special process that should be attached to every particle, because if a particle is missing this, I'm not sure there is any protection in Geant4 against missing transportation, because I was not sure.
I believe that now there is a check, yes.
Okay.
Not in earlier versions, but for several versions.
Yeah.
There is a check.
So you should, among the processes that you may attach to a particle, transportation is a process that should be attached to all of them. And basically it's a special process that if no physical process is taking effect, at least the particle will be jumping across the geometry, just taking into account the geometrical boundaries. As we will see, maybe we will see a bit later, but not now. And then finally, we have a reference physics list, which is a complete physics list, and they are ready to use. They include complete physics, and these are provided by the toolkit. And in principle, they are, as I said, ready to use and constructed by experts. Each prepackaged or reference physics list include different combinations of electromagnetic flavors with different degrees of accuracy and hadronic physics. Mainly, what is changing is the intranuclear cascade or the string model that is associated to those. These physics lists are used by some larger groups like Atlas, CMS, and other big detectors, but yet this does not remove the statement that the user is still responsible for validating this. And this is the reason when one is programming an experiment, you should always schedule some time of the experiment to be used for validating and calibrating your experimental setup, just to be sure that not only the equipment works as expected, but also to be used, for example, to validate a simulation. Okay, in this case, this is actually the code that we will implement shortly. This strange name represents one of the reference physics list. We will now go to the documentation to understand what it means, and we will retrieve the reference physics list out of the so-called Geant4 Physics List factory. So it will be something similar to the NIST material database, but for a physics list. Any questions so far? Okay, so we can take a look to the documentation just for you to have a, in case of doubt or to better understand what is going on. Okay.
Can you elaborate between the difference between atomistic and integral approaches to physics?
Yes, thank you for the question. So the idea is there are many ways to model how a particle interacts with matter. Geant4 may implement several of these processes and models. You will see the difference in the advanced course. I will not go into the details. The important thing is that there might be several recipes that would model the same physical event, the same physical interaction with different approximations or assumptions. And each one may have a different range of validity. Geant4 will not tell you, yes, this is the model that you have to use because this is the final truth. Geant4 will offer you a variety of these processes and models, and it's your responsibility to pick up the one that you think is best according to your needs. Some other simulation programs will give you only one option, and there is no escape from that. Then it might be a good reason because maybe they are implementing the best that exists, but there might be also a penalty because usually there is a balance between accuracy and speed up. If you want to use the most accurate model, probably this will require long computation time, and sometimes you can sacrifice part of the accuracy to gain some CPU time. So in the last word is the one of the user that has to say if some of the physics, the processes and models that one can retrieve, for example, from one of the reference physics list is good enough for that to simulate that problem or not. And that is the reason we always need to validate a simulation. I don't know if so in summary, there are several processes you have to choose that might describe the same physical interaction. And nothing prevents you also from implementing your own. If you think you can do better than the Klein-Nishina-Compton model 5D, you can implement your own and you can use it in your Geant4 simulation, replacing the whatever Compton model it is used in the Geant4.
We don't seem to have any takers today to implement a new model, so you can continue, I think.
Okay. So if you remember, this is the Geant4 webpage where we have all the user guides. We were checking already a few times the application developers guide, but there are others. One is the physics reference manual. We can open it just to take a look. And the other one is the physics list guide. The physics reference manual will include a long explanation of all the models implemented in Geant4. We will not go into the details. This will be reviewed in more detail during the advanced course. And this is the guide for physics list, contains a reference for the reference physics list that are offered by Geant4. We will use some of them. The naming is a bit complicated, and we will not go into the details. The default one that, let's say, is widely used in high energy physics and in nuclear physics, plus other additions, such as the radioactive decay, is the reference physics list, so-called FTFP_BERT, which corresponds to the string model FTF with pre-compound and the Bertini intranuclear cascade model, which only acts at high energy physics. There is nothing said about the electromagnetic physics here in the name. By default, the basic or the standard option 0 is used, but we can specify other options as we will see later. Okay, so now we can go back to the code and implement a physics list by yourselves. Okay, since we are going to use an existing reference physics list, we will not have to create our own derived class from Geant4 user physics list. We will simply take whatever the factory gives us. Okay. So, okay, you can see. Okay, so we can start by defining a variable that will contain the name of our physics list. It can be physics list name equal, and we will use ftfpvert. We will change it later just to see the impact. We will call the factory Geant4 phys list factory, Geant4 phys list factory. Factory, okay. And now we can create the object Geant4 modular physics list asterisk pl equal pl factory get reference physics list. Sorry for the long names. PL name. Do you think the code is correct as it is, or we are missing something? Good. Correct. We are missing the include. Do you think now the code is correct? Maybe it's included inside the Geant4 physics list factory. We will see. So if we go, I will keep the editor open, but in a smaller size. So you can type it. So if we go back to the terminal and we type make, at least the compiler was kind and was telling me what is the actual method that we have to use. Get reference phys is not get reference physics list, but get reference phys list. Sorry. In case of doubt, you can always go to the source code to be sure. Okay. We can run the executable. and it fails because we are missing the run manager. We can comment it out as we did before, just for the sake of playing. You don't have to do this. This is just for the moment. We can compile. We can comment up the call to the Geant4 run manager, get run manager, because it will keep giving the segmentation fall until we create one. We can make and we can run. Now the physics list is actually being created, and we see some output that is new. The new output is Geant4 Physics List Factory get reference phys list FTFP vert is actually instantiating the physics list and will be ready to be passed to the run manager. So I don't know if John and Gabriele, you agree, but from my side, I think it would be better to leave it today for now, and we can continue with the implementation of the primary particle and the run manager tomorrow.
People have had quite full afternoons already, so I think that makes a lot of sense. So let's see if there are any questions right now. I'll give the people a chance to ask a question, both from remote and in here.
Mm-hmm.
If you're in person, we can also help in case you're stuck from what's been done up to now. If you're remote, please reach out to us as well if you're stuck. What Alvaro has mentioned in the past is that he will upload the end of the day.
Yes.
You could, of course, use it to compare to what you have done. But if you've already tried to figure out something that you've done and you've got compiler errors or something else, it may well help you to understand how to address them by looking at them rather than just copying an answer. So by all means, reach out. I don't see any questions remote or in the hall. Everyone has understood everything or is too stunned or tired to ask questions right now. So I guess we will say thank you to everyone for joining today, and we will conclude the day as far as that's concerned.
Thank you.